In this video, we'll define the inverse of a function f. Let's suppose we have a function f that sends x to y. So I mean f of x equals y. The inverse of f is denoted f to the minus 1, and it's the function that sends y back to x. For this to be an inverse, it needs to work for every x that f acts on. Here's a simple example of how to work out an inverse function. Let's have f of x equals 4x. Now f of x takes a number and multiplies it by 4. And we want f inverse to take 4x back to x. Now this must mean that f inverse of x must divide by 4. So f inverse of x equals a quarter of x. Now we can see from this that since f inverse of x is a quarter x and 1 over f of x is 1 over 4x, that f inverse and 1 over f of x are not the same thing, even though the notation makes it look like they should be, because 1 over f of x is 1 over 4x, but that's not equal to a quarter x, because here the x is on the denominator and there the x is on the numerator. Let's work out another inverse function. This time we'll have f of x equals 3x plus 2. Now what does f of x do? Well, we start with x, we multiply it by 3 to get 3x, and then we add on 2. Now, since we want f inverse to take f of x and give us back x, to work out f inverse, we need to undo every operation that f did. So if we start off with x, first we undo the last operation that f did, so we take away 2, that gives us x minus 2. And before that we'd multiplied by 3, so to undo that we divide by 3. And that gives us x minus 2, all divided by 3. So f inverse of x, in this case, is x minus 2, all divided by 3. Here's one more example of how we can undo the operations of f to work out its inverse. Let's have f of x being 7 minus x cubed. And I'll rewrite this slightly to make it easier to work out. We'll have f of x written as minus x cubed plus 7. So now it's a bit easier to see which operations we're doing to x. We start with x, and we cube it. That gives us x cubed. Then we send x cubed to minus x cubed, so we times by minus 1. And then finally, we add on 7. So again, to work out f inverse, we start with x, and we undo all the operations of f. So we start by taking off 7 to undo the plus 7 bit. And then we'd multiply by minus 1, so now we divide by minus 1, and that gives us 7 minus x. And we started off by cubing, so this time we take cube root. And that gives us the cube root of 7 minus x. So this time, f inverse of x is cube root 7 minus x. Now we can also use algebraic manipulation to work out inverses. I'll show you how to do this with our second example, which was f of x equals 3x plus 2. Now remember that we want to take f of x and send it back to x. So if I set f of x equals y equals 3x plus 2, we want f inverse to take y and give us back x. So we need to work out how to get 2x from y. So if I write down again y equals 3x plus 2, I can rearrange this and I get y minus 2 equals 3x. So x equals y minus 2 all divided by 3. So to get from y and go to x, you need to take y, take off 2, and divide by 3. This means that f inverse of y equals y minus 2, all divided by 3. But that's just the same as saying that f inverse of x is x minus 2, all divided by 3. So this is how we use algebraic manipulation to work out inverses. Now we can use this method to work out some slightly more difficult inverses too. This time we'll have f of x being x over x minus 1. And we have to set x is greater than 1, because otherwise you'll get a zero denominator, so we only look at this function for x greater than 1. Now to work out the inverse again, we'll have y equals x over x minus 1. And remember again, we need to get to x from y, so we need to write x in terms of y. So we'll rearrange this. I'll multiply both sides by x minus 1, and that gives us y times x minus 1 equals x. And we want an x equals out of this with all the x's on one side. So I'll multiply out these brackets. You get yx minus y equals x. Then I'll take all the x's over to one side, so that gives us yx minus x equals y. Factor out the x, you get x times y minus 1 equals y, and that gives you x equals y over y minus 1. So here we have x in terms of y again, so f inverse of y is y over y minus 1, and that's just the same as saying f inverse of x equals x over x minus 1. So in this case, the inverse of f turns out to be exactly the same as f. This example shows how useful algebraic manipulation is, because it would have been really, really difficult to try and get this inverse by just reversing the operations of f. Not all functions have straightforward inverses. Let's look at f of x equals x squared, and I'll just quickly sketch you a graph if I can. Now when we look for an inverse for a function, we want to take a value of f of x and send it back to x. But in this case, there are two x's we could send f of x back to. That's because f of x is x squared, but f of minus x is also x squared. Now we can't define an inverse for a function if there are two things we could define each value to be. To get around this problem, we restrict how much of the function we look at. So instead of defining f of x like this for every x, what we do is we cut down the graph. We say f of x equals x squared, but only look at x greater than or equal to 0. And that gives us a graph like this. Now, since we've cut out all the values this side, each value of f of x only comes from 1x. So in this case, we can define f inverse. And f inverse of x is plus the square root of x. Now, we didn't have to define f for x greater than or equal to 0. We could have cut out the other half of the graph instead. So I could have defined f of x equals x squared for x less than or equal to 0, and that would have given us a graph like this. Now again, if I pick a value of f of x, there's only one value of x that gives us the f of x. So in this case, f inverse of x is defined, and it's equal to minus root x. Here's another function where we need to restrict the domain to be able to define an inverse. We'll have f of x equals sine x. And this graph looks a bit like this. I'll try and sketch it. So for x greater than 0, it does this kind of thing, then carries on forever. Then repeats itself down this way as well forever. Now if I pick a value of f of x here, you can see there's certainly more than one x giving this f of x. In fact, there will be an infinite number. So we'll certainly need to cut down the domain of this function to define an inverse. What we do in this case is we look at x for x greater than or equal to minus 90 degrees and less than or equal to plus 90 degrees. And if I block out the rest of the function, hopefully you'll be able to see that in this case, for every f of x, there's only one x giving that f of x. So for this, we restrict the domain to x is greater than or equal to minus 90, less than or equal to plus 90. And the inverse of sine x is called arc sine x. Now, this notation can be particularly confusing because f inverse of x, like I said before, is not equal to 1 over sine x. But you'll often see things like sine squared of x, which means sine x all squared. Just remember that sine minus 1 of x is not 1 over sine x, but the inverse function, sine x, which is also called arc sine x. The functions cos and tan also need the domains to be restricted for us to define inverses, but we cover these more fully in the trig functions video. There are some functions that can't have inverses, even if we do restrict their domains. A good example of this is a constant function, and that is something like, say, f of x equals 4. The graph of this looks like this. Now you can see here that the only way we could get 1x for each f of x here is to cut down the domain to a single point, and this isn't a very useful thing to do. So in this case we say that this function has no inverse. Now there's a nice easy way of getting the graph of an inverse function from the graph of a function. If I just get you a graph of some random function that I can think of. So we have x here, that's y, and I'll just draw some function that's appropriate, so something like that. Notice that a point on this graph has coordinates x, f of x. Now since f inverse sends f of x to x, we want the coordinates on the graph of f inverse to be the coordinates f of x, x, so these two interchanged. Now if I turn over this transparency so that my old x-axis lies where my y-axis was, and vice versa, let's do that for you. You can see by doing this, I've got precisely that. I've got f of x here and x here. So these points must form the graph of f inverse. So notice that in swapping these axes, all I did was I reflected down that line. The sort of bottom left, top right diagonal, I'm reflecting down here to get from one graph to the other. And this line is precisely the line y equals x. So that must mean that the graph of f inverse is the graph of f reflected in the line y equals x.